Hello viewers, welcome back to the course on scientific computing using MATLAB. So, today we will discuss about the error estimates in the polynomial approximation. So, today topic is errors involved in polynomial approximation. As we know that suppose this is my function. So, let us I plot this function. So, I take the sine function. So, let us suppose my f x is equal to sin x. Now, suppose the function sin x is not given to me, but the values of the function at some points that is given to me. Suppose I choose this point, then this point, then this point. So, I am taking the equispaced grid points. So, at this point this is the value of the function. So, this is the value of the function. At this point the value of the function is 0, then I have this value, then this value is given to me, this value is given to me, then this value is given to me. So, like this value is given to me. So, I have these points, so that I call it x0, y0, this is x1, y1, this is I call it x2, y2, and the same way I can go in the last one. So, suppose this is my xn, yn. So, these points are given to me. Now, in this case what I will do, I will take the polynomial interpolation. So, the polynomial interpolation will be what? Which is passing through all these points. So, I will start with from here, suppose it is passing through here, then the next point is here. So, this is the point, the next point is here, so it is going from here, then the next point is here, then the next point is here, passing through this point, then passing through this point, then passing through this point, and so on. So, this is my interpolating polynomial, and I know that if it is points, so I have a k plus 1 points, implies that the interpolating polynomial has degree less than equal to. So, this is not k, I should take it n plus 1 points, and degree would be always less than equal to n. So, now what is happening that this is my interpolating polynomial, and this red one is the actual function. Now, somebody asked me that what is the value of the function for this value of x. So, if I take this value of x, this is my value I am going to get when I put this point in the interpolating polynomial, but the actual value for this value of x was this one. So, from here I can say that this is the error involved in this case. Similarly, I can choose different points, and from there I can find, suppose I want to choose this point or this point. So, in that case, suppose I take this point from here. So, in that case you can say that this is my actual value and this is my approximate value. So, that this error is involved. So, I want to find out what will happen about this error when I approximate the interpolating polynomial passing through all these points. So, this is what we want to discuss. So, let us write down that, let us suppose that the values of a function. So, in this case this is my f x, which I have chosen as a sin x, are prescribed at n plus 1 points. So, that is given to me x0, x1, x2, xn, and value of the function is given to me at this point is yn. So, basically from here I can say that f at x naught is y naught, f at xn is yn. So, this is given to me. Then we can approximate the function f(x) by a interpolating polynomial so I call it Px of degree less than equal to n, because maximum degree is n. So, it is degree less than equal to n which passes through the points xi, yi's satisfying yi is equal to fxi. So, this is for all I is equal to 0, 1, 2 up to n. So, we can approximate the function f(x) by the interpolating polynomial Px which degree is less than equal to n, which passes through the points satisfying this relation. And you also from here you can see that at these points, the nodal points whatever it is given to me. So, at this point this function and the interpolating polynomial are coinciding. Only problem is to approximate the values in between these points. So, from here what I do is that I define the function. So, we can write the function f(x) as Px plus some error term. So, I call it Rx, where Rx is the error in the approximation. And what is the x is? So, x belongs to from x0 to xn. So, anywhere between the value x0 and x1. Now, we know that since fxi is equal to pxi, so that is already given to me. From here I can say that this implies that I can choose my Rx, that is equal to x minus x0 into x minus x1, x minus xn, and then I take kx. So, because at this point when x is equal to xi is for all i's 0, 1, 2 up to n, this is the same value. So, whenever this is the same value, the error will be 0. So, that is why I choose the Rx in this way. So, whenever I put any of the nodal point x0, x1 or xn, the error term will be 0. So, now from here I know that the kx is the function I have chosen. So, from here my equation number 1 can be written as, so equation 1 can be written as fx is equal to px plus Rx I can write as this one. So, this factors is a multiplication of all these factors. So, I can write this as a pi x minus xi, where I is moving from 0 to n. So, this is the sign of multiplication into kx. So, now I call it the equation number 2. Now, from here, now what I want to find? I want to find what is this kx. So, this kx I want to find. So, what I do is that let I choose a point x bar be any point in the interval x0 to xn open interval other than xi's. So, I want to find any point x bar which is other than this xi, because at xi this is same. So, I want to choose another point. Then from here I can write that this is equal to x bar is will be equal to p x bar plus, so I from 0 to n x bar minus xi into k x bar. So, this x bar is any point I have chosen. So, it can be any value. So, let us take this x bar is here somewhere. I will choose this value. So, suppose I take this is my x bar. Now, from here I can write this equation. From here I will get my k x bar is equal to f x bar minus p x bar divided by this x bar minus xi, and this I is from 1 to 0 to n. So, this is my x bar there. So, equation number 2 and this I take it 3. So, equation 2 can be written as f x is equal to p x plus k x bar. So, k x bar into now from the equation number 4, now we want to find magnitude of k x bar. So, this is I want to find. So, let us consider a function. So, I call it phi x. So, phi x I will represent like f x minus p x minus f x bar minus p x bar divided by this into pi x minus xi, I from 0 to n. So, I defined a function like this one. So, call it phi. Now, from here you can see that phi at xi. So, if putting xi x0 I am putting. So, this will be 0, and then from here this will again this. So, from here you can say that if I put f xi, it will be f xi minus p xi, then this part will be 0 because they are same, and this part will be 0 because here I put x equal to xi. So, this is also 0. So, plus 0. So, from here I can say that this phi f xi is 0 for all I from 0, 1, 2 up to n. So, this is there. Now, from here also I can write phi x bar. So, phi x bar if I choose, so this minus this and this part will be cancelled out. So, that this part minus this part will be 0. So, from here I can say that phi of x bar is also 0. So, from here I can say that my phi x is a function that vanish at n plus 2 points, because n plus 1 points are this and 1 point is x bar. So, apply vanish at n plus 2 points. Let us assume that phi x and its derivatives are continuous. So, I can apply the using Rolle's theorem. Phi x vanishes at n plus 2 points, phi dash x that vanishes at n plus 1 points. I am taking the derivative of this one, and so on. So, from here I take phi n plus 1 x. So, this is the n plus 1 derivative that vanish at 1 point, at least 1 point. So, let us call it xi that belongs to x naught to x n. So, from here I can say that phi at n plus 1 at psi that is equal to 0. Now, we have the equation in phi. So, the equation number 5. So, now we take n plus 1 derivatives of equation number 5. So, when I take the n plus 1 derivative of equation number 5, I know that this polynomial is of degree n. So, if I take the n plus 1 derivative, then its value will be 0. So, from here I can say that this will be equal to phi. So, that will be equal to f n plus 1 x minus 0, and from here you can see that this is just the constant value, but here it is a factor. So, if I take n plus 1 time derivative of this one, so I will get n plus 1 factorial from this. So, that you can verify from taking two factors. So, suppose I have a factor like this one, x minus x naught into x minus x 1, taking the derivative. So, I just take the derivative, I will apply the product rule. So, this first function derivative, second is 1 plus x minus x 1. So, from here I can get that this will be equal to 2x minus x naught minus x 1. So, this is the second quadratic polynomial. I am taking first derivative. If I take the second derivative of this, so that will be 2x minus x naught minus x 1, so that will be 2. Similarly, if I take three factors like x minus x naught, x minus x 1 into x minus x 2 and taking the derivative. So, this is the quadratic, this is the cubic. So, in this case, if I take the cubic derivative of this, then it will be 6 and this will be equal to 3 factorial. So, I am taking n plus 1 times derivatives of this factors. So, from here I will get, then this will equal to f x bar minus p x bar by multiply x bar minus x I from 0 to n, and this will be, I can write this as a n plus 1 factorial. Now, for x is equal to xi, I will get my phi n plus 1 xi. So, this will be f n plus 1 xi, and this factor will be same. The product n plus 1 factorial, and this die is equal to 0. I know from here. So, from here I will get that this is equal to 0. I will take this on the left hand side. So, from here I can write that f of x bar minus p x bar divided by x bar minus x I from 0 to n, that will be equal to f n plus 1 xi by n plus 1 factorial. So, from here now from the equation, and this factor I know the left hand side factor is, if you see from here, the left hand side factor is a kx bar. So, I can write that from equation 3 my kx bar will be f n plus 1 by n plus 1 factorial. So, this is the magnitude I am finding. Now, the above equation, so from here the value of the equation number 4 becomes, so from equation 4 I will get that my, or I can say from here that because my error is defined now, yeah, so this is my Rx. Now, from, so using this, now the Rx can be defined as x minus x naught, x minus x1 up to x minus xn, and the kx bar is f n plus 1 xi over n plus 1 factorial. So, this is the error. So, I can call it number 6, where this xi belongs to x0 to xn. So, any value between x0 to xn. So, this is my error. So, in that case you can see that first of all I should know the value of the function and its n plus 1 derivative. So, only then I can get this one. So, the from here I can find the upper bound also. The upper bound for error Rx will be, so in this case my Rx I can say that this will be less than equal to, if I choose this value x minus x naught, and if I choose this one, the maximum of this. So, if I take maximum of all values, x belongs to x0 to xn. So, what I do, I take any x which is the maximum of this value. So, all the maximum I choose. So, this Rx will be always less than equal to this. So, that way we can define the maximum, the upper bound for the error. It can be negative also, in that case I will take the modulus value. So, no problem, I can choose the modulus value, or I can from here itself I can say that this will be always less than this, the modulus value. So, that is gives me the upper bound for the error. Now, I want to define the, now we want to define error in Newton forward difference method. As we have done in the previous lecture, we have discussed the Newton forward method. So, I want to define the, that what will be the error in that case. So, the error in that case I can, or the same thing will be there, only thing is that I have to change my function f n plus 1 with the finite difference operator. So, I will apply this one. So, using mean value theorem, I can write my f x naught plus h minus f x naught, so that can I be represented by h f dash x naught plus theta 1 h, where theta 1 I can choose between 0 and 1. So, that is I can have from the mean value theorem. So, from here I can write this as a delta forward operator f x naught is equal to h f dash x naught plus theta 1 h. So, this is the function I have defined. Now, I can apply again. So, also we can apply mean value theorem again, and in that case I can write that f dash x naught can be written as h square f dash x naught plus theta 1 h plus theta 2 or theta dash I should choose theta dash h, where theta 1 and theta 2 or theta dash are all lies between 0 and 1. Now, from here I can write this as a h square f double dash x naught plus theta 1 plus theta dash h. So, from here I know that the theta 1 plus theta dash will be always less than between 0 and 2. So, from here I can write that this will be can be written as 1. So, from here I can write my second order finite difference forward finite difference operator as h square f double dash. So, this is the double dash I am taking is equal to x naught plus theta 2 2h. So, I call it as a theta 2. So, this way we can define. So, similar way I can define k. So, let us take it k, kth forward finite difference operator. So, it can be written as x naught is equal to h k f k times differential derivative of this function and x naught plus k theta k h. So, using this one from here I can say that now if I take, so this theta k I know that lies between 0 and 1. When theta k is 0, we will get this value will be x naught. When theta k is 1, in that case this value will be x naught plus k h. So, this will be k times I am forwarding. So, this is k plus 1. So, that is I can call it x k. So, now from here I can say that k times forward difference operator can be written as h k into f k some xi, where xi belongs to x 0 to x k. Okay. So, now we are able to define this one. So, from here I can write my f k xi will be equal to h k. So, this one I can choose where xi belongs to x naught to x k. Now, from the previous results, so this is my equation number 6. So, from the above results, using above results, equation 6, I can write my error function R x is equal to x minus x 0, x minus x 1, x minus x k. So, I am taking here the k value, and this I can choose. Now, my f n plus 1 xi will be same as the kth time the finite difference operator. So, from here I can write this as delta k plus 1. So, this f x naught is, I know that this is y naught. So, from here I can write this is equal to y naught divided by h k plus 1, and this is k plus 1 factorial. Now, from here I can say that the error involved in the Newton forward difference operator is this one. So, that is the equation number 7 I can define, and that is the error involved in the finite difference Newton forward finite difference operator. So, now we should stop here. So, today we have discussed about the errors involved in the interpolation when we have n plus 1 number of points in the given in the data, and we want to interpolate the interpolating polynomials. So, in the next lecture we will continue with this one. So, thanks for watching, thanks very much.